So we're here to talk about, can we rely on AI for critical tasks? We've heard so much about AI, all the things that AI is going to bring to the world, all the changes it's going to bring to the world. Yet there seem to be some challenges with AI and how we can, rely on it with critical tasks in particular.
I mean, I think as the whole world has been looking at artificial intelligence and AI in general over the course of the last couple of years since ChatGPT broke out, the focus has really been on chatbots, the AIs that you can speak to. I think the real next phase and what we're seeing emerging in 2025 is an entire shift towards autonomous agents, AIs that can do things for you. And all of a sudden, the stakes become much higher because with autonomous agents that will make decisions and perform actions for individuals, for businesses, for governments, the challenge we have today is that the current architecture, the infrastructure, essentially has challenges with respect to reliability, the hallucination problem.
So yeah, we've seen hallucinations, we've seen AIs making things up, but it's like unreliability, and often with a forcefulness that makes you think it's confidently inaccurate.
Confidently wrong.
Confidently wrong.
Yes.
So what is that about?
Well, I think back at a handful of examples over the course of the last few years. When Google, first launched, Gemini, someone went on and asked how many rocks they should eat per day, and they gave a very compelling argument for, a few little pebbles and one big rock might do the trick. Even just this last week, we were looking at one that it seems to really struggle when asked, is 29 degrees below or above freezing? And they said, well, freezing temperatures at 32 and 29 is above that, therefore blah, blah, blah. Now, is this the kind of AI you want running your cold storage facility?
How does that work in the real world when you're getting out in the real world? It's not viable.
Well, it doesn't work, and this is why The Economist has indicated about 5% actual adoption of these types of AI in real world applications, whether these are in enterprise for Fortune 500 or Global 1000, large industrial scale projects. We're seeing 5% take up so far. So even though lots of money is being spent to test essentially large language models to see if they can apply to the kinds of real world reasoning and planning challenges that we hire humans to do, they're coming up short.
So unreliability, you said unexplainable?
Well, that's the other problem. These are large correlational pattern matching systems. And as a result, they get bigger and bigger. So we go from, 1 million parameters to billions to now trillions. You couldn't put 1,000 data scientists in a room and have them understand all of the connections between these systems. Essentially, we're dumping all of this data with millions or billions of examples and hope that the algorithm will find the correlational relationships. But that doesn't mean that correlational relationship equals a causal understanding of the world. Right? So that's an unreliability issue. But as far as explainability, we can't tell why it's made a wrong decision. I mean, great example from just a couple months ago, you had these Waymo cars, which are quite impressive, driving around San Francisco, and a couple of guys rolled out to the streets with stop signs on their t-shirts. And they just opened up their jackets, they stood on the side of the road, and the car stopped in the middle of the street. Millions and millions of hours of training, more than any human, years worth of the equivalent of time, and you could trick it with a t-shirt. But over and over again, we see these challenges. And it's a fundamental problem with the approach that they're taking. But so you have this reliability issue, you have this explainability issue, and then the final one is efficiency.
Okay, and efficiency, on that front, we see the AI companies saying their largest challenge is electricity at this point. Their largest challenge is being able to power these large data sets.
Yes.
Are there other elements to that inefficiency?
Well, the brain uses 20 watts of power.
20 watts,
20 watts, like a small, very, very weak light bulb, right? You can have a banana and a glass of water, and many of the people that attend Davos are going to be talking about some of the largest challenges on the planet. What's happening in the mind of human beings, of biological systems, that doesn't require us to restart 3 Mile Island, which is what Microsoft is doing, or build $100 billion data centers So we've already exhausted all the data. Even Elon agrees with this. We've exhausted all the chips, and NVIDIA's still at all-time highs. And then now we're running out of energy. There's not enough energy in the United States, the grid. So we're talking to the Middle East, we're talking to Canada. Anything to build what we hope is a sort of super intelligence thing that will solve all of our problems. But there's something wrong with this underlying philosophy that's driving us to need all this energy. A smart system is smart enough to be efficient. And that's how evolution in biology works. And so that is a huge distinction between today's current approaches.
Okay, so if these are all the problems, is there a way forward? Is there a solution to this unreliability, unexplainability, and inefficiency?
Well, ironically, the solution is found in nature, in evolutionary processes, and we find that in the brain.
Okay.
So it's essentially the way that real neurons process information is hyper efficient. They do a very different kind of thing than what machine systems do. We kind of have this wrong idea about how brains work that's a bit of a hangover from the Industrial Revolution. We assume that brains are machines, or that they're like computers. In fact, it's very difficult to even talk about what the brain does without using some sort of metaphor like a machine or a computer. Oh, it processes information. The idea has always been in computer science, which came out of an last century idea of the computational theory of mind, that you passively take in inputs, you process them, you produce outputs. What the neuroscience actually proved over the last couple of decades in hundreds of papers is that you're a prediction system. And you're actually predicting into the future, and you're measuring the difference between that prediction and the sensory information.
So in other words, we're not an input machine making changes. We are adapting
in real time.
In real time to the environment in almost an evolutionary matter of
yes.
If I walk on this stage, is it going to collapse or not? It doesn't collapse, and then I will.
Yes. Intelligence is a balancing act of trying to make sense of real-time information and adapt and adjust accordingly. This is how we learn naturally. And this form of learning actually solves the reliability problem, the explainability problem, and the efficiency problem.
But how does that apply to AI? What does that have to do with AI? Because AI is taking these large amounts of data and making comparisons with it and coming up with answers,
well,
no?
I'll give you an analogy. So for 100+ years, we thought that the idea of a car relied on a motor and engine, gas and oil, right? Essentially combustion engine process. And then when Tesla came along, they said, well, what if we got rid of the gas, got rid of the oil, no engine and no motor, and we built a car that completely ran on a battery? And none of the biggest car companies in the world could do it. And in fact, if you told someone, it's hardly even could be described as being a car. The way we think about artificial intelligence today has very little to do with how the brain operates. But at Versus, what we've been able to do, in part because of the leading work by the world's top neuroscientists, who's Professor Carl Friston, our chief scientist, who leads a team of about 25 computational neuroscientists in our company, have uncovered this natural process of learning that occurs in the neurons that allows it to model the world in real time, make these predictions, and then test cause and effect. So it becomes more reliable over time. It does it in the most efficient way. And because it's predicting what it's going to do next, we can actually see what it's thinking, and therefore its predictions are explainable.
So this thinking, this take of AI based on this evolutionary process came from Friston and his lab and the look of his study of how the brain actually works.
Correct.
As opposed to an engineering of AI via statistical databases.
Correct. And so what we've done is taken the universe of neuroscience and everything that we've learned in the state of the art of the field and applied that to the state of the art of computer science. And so what Versus is doing is combining these two universes together and saying, can we apply the blueprint that we see in nature, in evolution of natural learning, to autonomous agents, to intelligent AI systems that are far more adaptable, far more intelligent, and far more sustainable.
And do you have any proofs of this? What are concrete examples of how you've applied this?
Yes, actually, there are several, but today I'm very excited to share that there is a kind of industry benchmark test. It's called the Atari test. You might recall back in '96, Gary Kasparov loses.
I recall Atari. I'm a little bit older, a little, I confess, I do remember Atari.
Well, back in the '90s, the whole kind of vision of could we get an AI to surpass humans at
Gary Kasparov,
games? Gary Kasparov loses, to Big Blue. '96, 2016, I believe. Go, which is a much more complicated game of strategy. Lee Sedol loses to Google DeepMind's AlphaGo model. Then the question was, well, what about interactivity? Not just sort of games or puzzles, even though the most recent ARC AGI test that OpenAI won is just a kind of a puzzle. What about interactivity? And can you do it across multiple games? So this is called the Atari test. And the original ones use billions and billions of samples of the game with Google's model, which is called Atari 57, which would be the equivalent of trying to learn to play these Atari games in like 11,000 years in human lifespan. This sort of brute force approach that we still sort of see in LLMs today. And then the industry said, okay, this is a sort of Olympics of AI, but we need to learn more like a human does. So let's limit it to something not like 11,000 years, but 2 hours, what's called the Atari 100K test. All the top models in the world, the transformer architecture, which is used to underwrite all of generative AI from the image generators to the chatbots of today, and the deep reinforcement learning ones that underwrite a lot of stuff like autonomous vehicles and humanoid robotics, are all tested in this 100K test, Atari 100K. We said, well, if our theory is correct, we should be able to beat them with 10K.
So 10K meaning 1/10?
1/10 of the data, 1/10 of the compute, and equal or
and so you put versus up against
the transformer model, which is called Iris. There's bigger, better, faster, and efficient zero, which are versions of Alpha Zero that came out of DeepMind. And today we're happy to share that the results actually match that. We were able to demonstrate superior performance, in some cases even perfect play, beating both the game, beating human scores, and beating the competition with a fraction of the data, a fraction of the compute.
So this is DeepMind. This is who are the?
These are the underlying algorithms that DeepMind has used for AlphaZero, that OpenAI and everyone else uses for ChatGPT and the rest of these sort of systems. So the underlying algorithms that power those systems, that are what we call AI today, our biologically driven approach that comes out of the sort of neuroscience field has demonstrated a hyper-efficient, hyper-performant, and explainable approach.
So reliable, explainable,
and more efficient. And this is a paradigm shift in the whole future of AI. We think about autonomous agents that need to not just be one giant super agent that some company in Silicon Valley develops that we're all supposed to connect to, and that's in a $100 billion data center. Mm-hmm. Now you're talking about the ability to have agents on 100 billion different devices. So small they fit in your pocket or on a camera or in a drone or a car that can make decisions in real time at the edge. This is a complete paradigm shift in computing, as different as the shift from supercomputers in the 70s to the personal computing revolution we saw in the 80s.
So, but basically you're using an entirely different approach to AI. One of them is more of a pattern matching approach.
Yes.
Of all the data, massive data set that we're using expensive chips to plow through using a lot of electricity. Yes. versus your company name, versus using more of a reasoning approach built on neuroscience.
Yeah, and this has been the big gap for what we want from autonomous agents, what's called reasoning and planning. And what is reasoning? It's inferring cause and effect, right? And I have to be able to test cause and effect in order to know. These large language models are trained, they're pre-trained, and whatever's in there is all you get.
It's historic data, actually.
Exactly. In fact, their latest reasoning model was another test that we did called Mastermind with their O1 model, which is one of their latest production model. We tested it against our algorithm, which we call Genius, and we beat it at this game called Mastermind. It's kind of a code-breaking test.
Atari era code-breaking test.
Yes. So beyond Atari, this is sort of, beyond the underlying algorithm, let's test the actual products themselves.
Right.
And all of a sudden we were able to, demonstrate extreme efficiency. We did it 140 times faster. It cost us about $5 to run 100 games side by side against theirs. They cost about $246, so about 5,000 times cheaper. And we were 29% more accurate. So again, more reliable, more efficient, and the explainability just comes with it because as it's predicting its next steps, we can see it, which means we could say, that's a great idea, please don't do it.
Fantastic. So it sounds like we're entering this era of new flavors of AI versus offering up one which is based on neuroscience. You're not basing it on massive amounts of historic data. You're basing
Correct.
it on the algorithm, understanding the world, testing the world, seeing if we can walk across the stage and it doesn't collapse. And if it doesn't,
That's how we
then
learn
we've
to balance.
learned it.
That's how children do it. That's how children learn to identify cats. They don't see a million examples. You kind of learn step by step, progressively. And that way you can constantly be learning and constantly be improving. You don't have to go back and retrain these models. So you even get compounding efficiencies over time. But think about it, GPT-3 is gone. They trained it, it cost $500 million, it's gone, right? And now each time they're saying it's gonna cost 10x more to get some incremental linear gains. We just think that there's a better alternative now, and it comes from following the blueprint that nature has laid out and that evolution has sort of indicated to us.
Fabulous. Gabe, thank you so much.
Thomas, thank you for the
Fascinating
time.
conversation. Let's give a round of applause to Gabe. Thank you.